Hello everybody, welcome to this second video about the viscous flow analysis around an airfoil. In today's video I'm going to show you how to calculate or to actually how to generate the geometry of whatever Naca 4-digit series airfoil you want. So let's get started right after the intro.
It's one small step for man, one giant leap for mankind.
So a Naca 4-digit airfoil, what is it? Basically, airfoils can be defined by a series of numbers. They could be, I don't know, they could be like 3, 4, 5, even 6, for example, digits. And they're called Naca 4-digit airfoils because these were basically defined by Naca, which is actually was basically the National Advisory Committee of Aeronautics, and it was replaced by NASA afterwards. In order to better understand what we're going to do, we need first to define or understand a bit how an airfoil is made. And we can distinguish the following characteristics. So I would start first of all by by identifying what the um, upper surface is, so the top of the airfoil and the bottom. Okay, so between the upper and bottom surface of the airfoil, we can identify an imaginary line, which is at equal distance from the top and the bottom. This line is called a Camber Line. Okay, and this is very important during the construction of the geometry of the airfoil. Then we can identify, for example, the leading edge, which is basically the point of conjunction between the upper and the bottom in the front part of the airfoil, and then we have the trailing edge, which is the same but at the end of the airfoil. And third thing we can define is the chord. The chord line is the line, it's a straight line that connects the leading and the trailing edge. And finally, we can also identify the thickness of the local thickness of the airfoil, which is basically perpendicular to the camber line and extends from the top to the bottom of the airfoil. A thing that I didn't put here is actually the angle of attack. The angle of attack can be understood basically as the angle between the relative flow of the airfoil and the chord. So imagine that the wind is coming from like sideways, like this way. The angle of attack would be the angle between the chord and the direction of the relative wind. For the Naca 4-digit series, for example, the Naca 4418, which is the one that I'm going to use to make to walk you through the code. We can see that there are actually, 4 numbers, right? 4418. What do they mean? They have a meaning. They're not like random numbers, of course. So let's start from the first one, the number 4. So the number 4, which in my case I defined as M, is the first digit and describes the maximum camber as percentage of the chord. So the maximum camber is actually the distance, this distance here, okay, the maximum one, so it would be somewhere here probably, divided by the length of the chord, okay, so it's a percentage. Then the second digit of our 4418 is again 4, and describes the distance of maximum camber from the airfoil leading edge in terms of the chord. So imagine that the maximum camber is here, okay, from the leading edge we have this distance, and it's expressed as tenths of chord. Finally, we have the last two digits. I called it SS, but in our problem is 18, basically. The last two digits describe the maximum thickness of the airfoil as a percentage of the chord. So the maximum thickness, let's suppose it's somewhere here. Okay, we have the maximum thickness in as a percentage of, again, of the chord. Good. Now, yeah, let's suppose that we do not suppose, we have actually these three parameters. Yeah, they can be plugged into this equation, this polynomial equation, and this will give us a variable y, which is actually which describes the airfoil thickness. Okay, as a function of x, which is the chord, basically. So if I want to know the thickness of the airfoil, somewhere here, I plug it into this equation, and if I also know the x, which is the chord, I can also know the thickness of the airfoil in that position. So the camber line C and the gradients are calculated according to this equation. So the camber line, once again, is this line here, and the derivative, and the camber line is defined based on the, we can distinguish the front part and the back part of the airfoil, which is defined by the parameter p. So if the chord is less than the value p, then we can consider that as the front part of the airfoil. If x is greater than p, so we are in the back part. So based on this, we can apply these two equations to calculate the chord. The camber, and then we can calculate the derivative of along x, so along the chord, yeah, and we have the derivative of this is this, and the derivative of this is this. Yeah, I hope so. At this point, if we know the chord, yeah, and its derivatives, and also the thickness of the airfoil, we can calculate the upper and the bottom of the airfoil, because basically we know the camber line, okay, how it's shaped, and we also know the thickness, right? So if we know thickness and camber, we can also calculate the external surface geometry, which is actually what we want. Okay, so I think now we can get started coding. So let's get started by defining, okay, a variable called Naca, and it's going to be a number, okay, because it's a 4-digit series. So our Naca is how do we define it? Yeah, 4418. Okay. Now, once we know the Naca, we have decided which Naca airfoil we want to use, we can define also the dimensions or the parameters that we defined above here. So let's get characteristics, dimensions, characteristic dimensions as percentage of the chord. So what do we have? We have m, which is the first digit of our Naca, and since it's a percentage, okay, we need to divide it by 100, so it's 4%. Then we have phi, which is the distance of maximum camber line from the airfoil leading edge in tens of chord. So what is it? It's Naca 1 divided by 10, and then we have SS as Naca from 2 to the end, divided by 100. So first step is done. We have the characteristic dimensions of the airfoil. Very good. Now, what do we need? We want to calculate y, right? So we have s or double s, and we need x, right? And x to have these values. So x is the core, right? So let's define. We're gonna define in this case a unit chord, like that goes from 0 to 1, but you can make it whatever length you want, actually. In this case, I don't have like a specific dimension. I want to make this airfoil, and therefore a chord of 1 is good enough. So let's define a unit chord as C, and here we have to import a library called Numpy. So import Numpy as NP. So this library will help us to have more mathematical functions, and it's very helpful. So the Numpy library has the linspace function, which creates an array that can go from 0, for example, to 1, and we can divide it into as many points we want. So how many do we choose? Well, for this, I think it's useful if we define an input, like a number of points. I will call it number of coordinates, and we can set it to, I don't know, 300 points. Okay, so number of coordinates will be 300, and yeah, that's it. Good. Now we want to calculate the airfoil thickness. So calculate the airfoil thickness. It's our next step. And we know it's y, and it's defined according to this equation. So again, keeping this in mind, we know it's 5 times SS times what? Parenthesis 0.2. I'm gonna read it from my notes. 0.29690 times what? Pi, and here we have a square root of x, so numpy dot sqrt of x, or sorry, of c in this case, because x is equal to c for us, and yeah, minus 0.12600, doesn't matter, times c minus 0.35160 times c squared. So for c squared we can use again numpy as let me check, numpower, yeah, as np dot power of C power 2, yeah, plus what? Plus, we're almost done, yeah, 0.2843 times Numpy power C, so power 3 of our chord, and last one is 0.10150 times and p power again C comma 4. Let's see if this works. Yeah, it looks like we have an error. Yeah, so int object is not subscriptable. What does it mean? That if we have a digit, number, actually, if we have a number like this in Python, we cannot like get its single digits in this way, okay? So we need to make this as a string. But if we make this as a string, when I do Naca 0, I will get number 4 as a string. So I need to convert back to an integer. So let's do this for all of them. Right? So there we are. Good. Then we have a typo here. It's linspace. Good. Yes, it looks like Python is not giving us any error. And if we do Control Shift to run the code, then we can see the Y. So this is the thickness of the airfoil. And we can also calculate the length of this array and see that it's 300 points as we wanted. Very good. So now we are done with this part and we want to calculate the camber line and its gradient. So we need to implement these equations here. So let's do that. It's very simple. So calculate camber line and gradient. Good. So let's do it. It's very simple. We do first of all, I'm gonna split the airfoil into a front and back part. Okay. So I'm gonna define a letter F as forward or front, and it's gonna be the camber line when the camber line is less or equal than P. Okay. So I'm saying what I'm saying here. The front part of the chord is all these points of the camber line that are less than P. Okay, so if you don't know what this is, then please write it down in the comments for those maybe who never used Python. And I hope somebody I would can help you in the comment section, and if they don't, I hope I will be able to do it. To explain why this is written this way. I am actually assuming that most of you have a basic knowledge of Python. Okay, so we have forward here, or front, and then we can make a back. The back part of the airfoil, which is everything that is greater than P. Good. Then let's implement the equations. So the first one is this CF here. Okay. CF is equal to CF M divided by what? Numpy power of 2, P squared, sorry, P squared, times what? All of this times 2 times p times c minus p power of c squared. Good. Now we can calculate the derivative. The derivative is dcf equals to what? Or let's calculate actually the back part first. dcb equals to m divided by, and we can see it here, 1 minus power, no, sorry, 1 minus p, okay, but it's square, right? So we need to do np power of 1 minus p, comma, and here is gonna be 2 squared, yeah, times what? All of these times parentheses 1 minus 2 times p plus 2 times p times c minus power of what? Of c squared. Okay, good. So we got this, yeah, right? And now we can calculate the whole Camber line as the combination of the front and the back part, right? So again, we can use what? We can use the Numpy library concatenate, and here we can have a tuple. If you don't know what a tuple is, it's a basic, it's a variable type for Python. Now we can calculate the complete Camber line as a concatenation of the front and the back part that we just calculated. So we can write it within a tuple as for Camber line forward and Camber line back. Okay, and we need, what else do we need? Yeah, define axis equals to 0, which means that we put one, we continues basically the CF array with the values of CB. And now we're missing the derivatives. The derivatives, we have dfc, okay, so again, df, so now we can calculate the derivatives that we see here, and the first one can be calculated as the C forward, which is DC forward, okay, 2m, 2 times m, divided by Numpy power of p squared, and all of this is multiplied by what? By p minus f, right? Yeah, the front part. Mistake. There's a mistake in all of this actually. This is not C but F, because here we are calculating the upper part, the front part, and here instead of C we should have B. Yeah, now it should be correct. Okay, and now we can calculate also the C back end derivative of the back part, and this is what? this is equal to basically all of this, and here instead of having p we have 1 minus p, yeah, squared times p minus b, not 4 but b. And finally we can put together the forward and the back part of the derivative of the Camber line in one single variable, which we can call dc, and it's concatenation of dc and dcb. Perfect. So let's run. We don't have any error. Good. We're almost done calculating the geometry. So we have everything we need to calculate now the angle theta and the coordinates x, y of the airfoil itself. So let's do that. Calculate upper and lower surface coordinates of the airfoil. How do we do this? Well, let's do theta is equal to what? Again, we can use Numpy, and Numpy to calculate the arc tangent is arctan of what? Of dc. Oops, dc, yes. And then we can do xu, so which is equal to c minus, so the chord minus y, the thickness, times Numpy, Numpy cosine, or sorry, sine of theta. Xu here, right? And then we have yu, which is equal to the Camber line, c, big C, plus y times cosine of theta. Good. Now we need to calculate also the lower part, the bottom of the airfoil. So we're gonna call it XL, YL. Good. And these are what? So here we have a plus. Oops, plus, and here we have a minus. And we should be good. So last part of this is to put together the upper axis and the upper and lower axis and the y and the y's. So let's do that. And we have x, which is np concatenate what? Well, here we need to be careful because the upper part, okay, if we follow the method that I just used, we go from where? We go from from left to right, and also the lower part, the lower coordinates will go from left to right. And yeah, even though this is like okay, no problem. When we plot it, actually it doesn't. It can create some problems. So we want to have a plotting that follows a circular motion, right? Circular pattern. So we need to flip the coordinates in such a way that we have one part that goes from left to right and one that goes and the lower part that goes from right to left, or vice versa, whatever you feel like. So we have to like flip the array, and here we have flip what? XU, and we concatenated with the X lower. And here we have X is equal to 0. Good. And same thing needs to be done for the Y. So the Y coordinate needs to be flipped in the upper part. And let's test it. Okay, DC is not defined. What does it mean? DC. I don't see it. Yeah, it's big C. Okay, and then here also we have an error. We don't have Numpy used. Same here. Good. All right, we are almost done generating the geometry. So let's continue. And in order to check our result, we need to plot the airfoil, right? That's what we would like to see, and to make sure that our result is fine. And in order to do this, we need to import the Python library called matplotlib. Okay, so we can import matplotlib, and from here we can create a figure where we have our airfoil. So let's do that. Let's use the matplotlib library to make a figure. And this figure, we can define the size. So fig size is equal to what? We create a tuple, and I like 16 as a width and 9 as a height. And then what else? Plot equal plot. So we're going to plot the variables, so x and y. And I like to make it what? Like a dash line. And it's gonna be like blue dash line. And we're gonna have a label equal label. We're gonna label as a surface, airfoil surface. Then we don't want to see only the geometry, but we want to see also the camber line, for example. So we can do plot, again, sorry, plt.plot, and we're going to have as an x the chord, yeah, and the camber line is the big C. And we're going to make a red and dashed again, dash line, and name it Camber Line. Camber. Yeah, I think it's correct. Now, what I like usually is to have the axis of the plot equal, and in order to see like the shape as it should be, and it's not form. So in with matplotlib we can use GCA. And here we can set the aspect ratio, which is equal. And let me check, equal adjustable box. Adjustable equal box. I think it's correct. And then we want to have also legend. So PGCA, let's set the legend. And also I want to have the X and the Y label. So plt dot X label, and the label for X is actually the letter X in my case, and I don't have any units because we started with a unit chord. So, and if you want, you can use also some scale it to some different size and use whatever unit you want to use, basically. And same for the Y, no problem. We can add also title. So plt dot title, and the title is gonna be what? It's gonna be airfoil. I like this, airfoil, Naca, and then we're gonna use this way of creating the title. So, oops, yeah, we're gonna use format. And format, what it does, you use these parentheses here, the curly brackets, then you do in your string, then you do dot format, and within format you write down the thing you want to display within the bracket. So in our case, it was Naca 4418. Good. Um, and yeah, then finally, if you like, you can also save the image. So you can save fig. I'm not gonna do it, but you can. And one thing I want to show you here is if you wanna save an image, one way of doing this is importing the library called OS and use, for example, os.path.join, and within you can write first variable, which is the path where you want to save your image, so or the folder basically where you want to save it. For example, in my case would be images, and the second variable is in figure the figure name, so the file name actually of the image. For example, we can do Naca plus what? The file name could be .png. So we take the Naca name and we add .png to save it as a file. And we are good. We are good because now last line of the code is plot.show. Good. Are we ready to see what happens? Nothing. Yay! There it is. It worked. No errors. And here we can see our Naca airfoil, and it's looking good. The chord line is a unit from 0 to 1, and yeah, it looks nice. So what I would like to show you now is one last thing before we end this video and we move on the next part where we're gonna improve this code a bit more using methods and classes and so on. And it's the case where we have the Naca 0012, and the problem with this Naca is that the second digit is 0. And if it's 0, it means that we may have division by 0, which obviously we don't like. We cannot divide by 0. Therefore, we can use the final line of code to add like a very, very small number, this possible smallest number that the computer can use, which is not 0. In Python, we can use this line of code, f-infofloat.apps, which is, I think, called machine epsilon, I don't know, something like that. Let me see. Epsilon machine, I think. Yeah, it's called epsilon machine. We can add it, and then we don't have more this division by 0. We can complete the whole shape of the airfoil. So thanks for watching, and if you have questions, please code it below in the comment section, or let me know if if you guys have any doubts or if I can help you out somehow. And I will see you in the next video. Thanks.